Sorry, we seem to have lost Mike, so we're just trying to get him back 1 second. But in the meantime, we will move on to the next speaker and then come back to Mike when he is back with us. So our next speaker is Amanda Prorok from the University of Cambridge. So thank you very much, Amanda, for joining us. Let's just make sure you are spotlighted. Brilliant. Hi, Amanda. We can see your screen and everything wonderfully, so thank you very much. So thank you for joining us, and I'll hand over to you.
Thank you. Can you hear me as well?
Yeah, very clear.
Super. Well, first of all, thank you very much for inviting me. This is a really exciting conference. So hello, everybody. My name is Amanda Prorok. I'm an associate professor at the University of Cambridge. And today I'm going to be giving you also a very quick tour of the work we've been doing towards learning to communicate in multi-agent and multi-robot systems. See if I can actually advance here. There we go. So one of the key ideas that really drives the research we do in my lab is the idea that the whole is greater than the sum of its parts. And this is an idea that you will encounter in many collectively intelligent systems where we observe emergent behaviors that lead to the agents visibly completing very complicated and complex overarching tasks and goals. And so what we're striving to do within my lab is to endow autonomous agents with components of intelligence or core capabilities that enable them to, at the end of the day, cooperate, coordinate, and collaborate. And we do view these three different activities as three distinct ways of getting autonomous agents to work together to achieve overarching goals. And what we find, or what one of our key premises is in our work, is that communications is a key means towards this end. And so a lot of our effort and work goes towards devising the communication strategies that would enable our robots to do these cooperative, coordinative, and collaborative behaviors. And where does this all feed into? Well, we really believe that the next wave of computing is about agents that communicate, and you'll see this idea cropping up in numerous and multiple different application domains today that are already deployed, not only in development, but actually really being executed within the commercial sector and private sector as well, to a great extent and also very successfully. Most well known to you will be the area of logistics and warehouse automation, but we're also seeing it become viable within transport and agriculture domains. And of course, there are a little bit more far-reaching visionary ideas where we're thinking of construction, space, and perhaps more low-hanging fruit environmental monitoring and surveillance applications. So these are all extremely successful examples, but the key point here is that whether it's through simple coordination or more sophisticated forms of collaboration, these systems do really perform better when there are several robots contributing towards the overarching goals. And so we're really interested in understanding how we can get the robots to work together. And that question, from our perspective, boils down to the question of how can we get the agents to effectively communicate in order to achieve these coordinated behaviors. Now, it's not such a simple problem because there are numerous challenges or hurdles that we have to overcome to really making this a reality that we can deploy reliably into the real world. The first problem is that coordinated decision-making is actually a hard problem. It's computationally hard. The second issue is that as soon as you want to decentralize these processes where the computation is essentially sitting within the individual nodes, we need to facilitate communication between the nodes. And then the question is, well, what are the individual agents going to be telling each other? What is the communication? What's purpose is the communication trying to serve here? And finally, if we're relying on communication for these agents to be able to coordinate and work together, what happens when communication just doesn't hold up? What happens when it's noisy, when there are delays, when there are faults, or when messages actually never reach their designated recipients? And we need to think about all of these issues as we devise algorithms that deliver the communication strategies. So of course we can go and design first principles-based approaches towards this, but we have found through prior experience and also through a whole body of research that first principles approaches are difficult to come by because A, more often than not, they have to be designed on an application-based basis, and they have to be tuned with respect to every single individual application we're targeting. And finally, once you have a framework set up, it doesn't necessarily generalize well across different tasks. So we're looking towards data-driven approaches in the hope that we can generalize better across tasks, and that we are able to design frameworks that allow us to more efficiently design or distill communication strategies and communication coordination policies that we can then maybe apply to a wider set of problems where we want coordination, collaboration, and cooperation to happen. So I've summarized a bit of the research problem. I've distilled it to problems of hardness, decentralization, and robustness. And I've alluded towards the fact that we're using data-driven methods, so machine learning-based approaches, to get around a lot of these challenges. Now, our workhorse within the field of machine learning is an architecture that is known as graph neural networks, because the mathematical formulation of graph neural networks really elegantly allows us to devise formulations that are efficient for learning, but that simultaneously lend themselves very naturally to decentralized decision-making agents. So the graph neural network formulation is one that is intrinsically decentralizable. We train these networks through various machine learning paradigms. So reinforcement learning and imitation learning are the two common paradigms that we rely on. And our goal is usually to try to reach performance that would be comparable to that of a centralized near-optimal solver if we have one. Yet in our case, scale more gracefully in the case where we're trying to, for example, scale to very, very large agent numbers, or in the case where unpredictable events occur and optimal centralized solvers are not necessary designed to deal with such cases. Emergent robustness would be one of the properties we would be looking for. So I'm going to walk you through a couple of problems that we've solved and try to give you a bit of an insight to the underlying solution and methodology. So the first problem that we tackled was this problem of multi-agent pathfinding, where the research question we set ourselves was, can we actually automatically synthesize the local communication and decision-making policies to solve computationally hard coordination problems? The reason we actually went for multi-agent pathfinding as one of the first problems we tackled was because we had centralized solvers that we knew were optimal and we could solve for in the case of relatively small multi-agent systems. And this allowed us to benchmark in a very reliable way how well our graph neural network-based approaches were actually working. And so we started off by designing an architecture that allowed us to train through imitation learning a decentralized policy that would then run locally on individual agents. And we compared the policies that we were able to train with the performance of the optimal centralized solvers that we used in the first place to train them. Now, the key difference here is that on the left-hand side, so you can see the movie playing out where we're actually comparing these two solutions. On the left-hand side, we have our expert solver, which is running based on entirely observable system with centralized knowledge. So it's an optimal solver that bases its planned actions on full state information of what's going on in the system. And on the right-hand side, we're showing our solution where the policies are essentially running on board the individual nodes of the system. And the agents themselves only have a limited field of view. So they can only see the agents that are within their immediate vicinity, and they actually only see the environment that is within their immediate vicinity as well. So they have a local field of view. The agents don't even know where they are within a global reference frame. They only have a direction within which they know their goal lies. So they know where they have to head roughly, but they don't exactly know where this goal lies within an XY frame, for example, and where they are within this XY frame. So extremely limited information. And what's really astounding here is that you can see that this policy that we derive through imitation learning is able to exploit communication in order to not only avoid collisions and deadlocks with other agents, but also to learn about the environment so that the agents eventually progress towards their designated goals. And so this is really phenomenal for us because we're showing that decentralized systems based on data-driven methods can achieve performance that is very, very close to optimal solvers that take a significant larger amount of time and computational resources to solve.
Amanda, I'm so sorry.
Yeah.
Sorry to bother you. We just seem to be having the screen is quite blurred. I don't know if you could just maybe try turning off your video or re-sharing just to see we can't quite see the videos and the text. I'm so sorry to interrupt.
I'm going to actually, what I'm going to do is I'm going to turn off the video optimization. I'm going to share again. That's probably what it was.
It was fine until the last recent slide.
So let's just try. No, thanks for mentioning it. I'm going to try again without optimization for the video clips.
Perfect. Thank you.
And we'll go again. Appreciate you mentioning it. So let's see.
Oh, so much better. Thank you.
Okay. All right. Hope that plays a little bit better. Appreciate you mentioning it.
Really good.
So what you can see happening here is basically on the right-hand side, agents with their local communication neighborhoods. And the graph neural network-based policy that the agents learn has taught them how to integrate these messages and make decisions based on this incoming information so that they can decide how to effectively and efficiently reach their designated goals within these environments. And I just wanted to point out that in the 2021 paper, we actually added an attention mechanism to our graph neural network baseline policy that allowed us to generalize these systems to 10x or 100x in terms of number of agents with respect to the system sizes and scales they saw at training, showing how this architecture actually has the potential to generalize way beyond the problem instances that it has seen during training time. And this is really interesting to us because, for example, if we use these optimal solvers, we know that given a computational timeout of, say, roughly 10 minutes, we're at a limit of in the ballpark of 40 to 50 agents. And that is really small when we're trying to really scale up to larger areas and larger systems with more complicated tasks. So another thing that we did was look at how we can leverage reinforcement learning paradigms in training to get different types of emergent communication behaviors. And what we tried to do here in this case study that I'm showing you here is, well, on the first hand side, we tried to see if we could train these multi-agent systems to learn how to cover non-convex environments. So what you see playing out here is, I hope the movie is playing, is on the left-hand side, a fully cooperative multi-agent system that has learned to distribute very effectively within this environment so that they, as quickly as possibly, cover the environment fully, whilst communicating with each other in order to achieve this coordination. Now, what is interesting is that if we decide that we're going to train the system slightly differently, where we don't train all the agents simultaneously, but instead alternate the training where the agents have exactly the same incentives, funny things start to happen. So in this case, on the right-hand side of the movie that I'm showing you, we actually alternated the training between red and blue agents. All the agents have exactly the same incentive, which here says you get rewarded for every new cell that you cover. But simply, given the fact that a certain agent's policy is able to train while other agents' policies are fixed, means that it is exploiting its communication channel to manipulate the other agents to go into the regions of space that are either already covered or are of no interest to the agent currently learning its policy. So you can see on the right-hand side how the red agent here is really exploiting its communication strategy or its communication channel to keep the blue agents in check and keep them in the lower hand side of this non-convex environment so that it can reap the benefits or the rewards it gets from covering as much area by itself as it can. Okay? So this is just showing you how careful we have to be with our learning paradigms when we're actually trying to achieve cooperation and what kind of scenarios we want to avoid if we really want to avoid non-cooperative behavior, as you can see here. In this slide here, we actually went in, and what I'm showing you here is what's going on under the hood with this emergent adversarial communication. And we were really able to confirm that the agents that learn to be manipulative are manipulative because what they are sending really does not correspond to the ground truth coverage that they actually executed. So they're telling the blue agents that they actually covered area that was not covered by them. And thereby are misleading the agents, the blue agents, into believing that they should go cover certain areas in space, which actually are of interest to the agents. So this post hoc interpretation came in really useful to us to understand what these black box methods are actually doing under the hood. And so the last thing I just want to show you before I wrap up is something that actually is running on actual robots, because up to now I've been showing you how we're doing all of this training in simulation with agents that live in a simulated world. And at this stage, you're probably asking yourselves, well, actually, do these policies transfer to the real world? And this hasn't really been done much before yet with policies that are derived through graph neural networks. And so we decided to actually evaluate what the bottleneck might be in doing so. And the question here was basically trying to understand, are the communication distributions that the policies are seeing during training similar to the real world communication conditions that they encountered during deployment? And so we went through this step by step, first using a managed centralized communication network, relaxing it until we had a completely ad hoc point-to-point communication network, and we're running policies on board locally on every single robot in this case study to see whether or not the policy would actually hold up with the fully distributed setup. And the good news is that we were able to show that, for the managed network, as well as for the network that was exploiting certain centralized components, it worked really well. But it also really worked well when we deployed it in fully decentralized mode, with execution decentralized, as well as communication running in a completely decentralized ad hoc mode. And so the robots here were effectively being trained to pass through this constriction whilst coordinating with one another in order to get to their destinations as quickly as possible. And so we're really happy about the status quo in the sense that we know how to devise graph neural network policies. We've made inroads to transferring those policies from simulation to the real world. And now we're essentially thinking about, okay, what can we do with all of this? And there are many, many things we're excited about. I've just listed 3 topics that we're excited about. So the first one is running into the same direction that I alluded to before. Are we able to explain what our agents are learning? And are we able to explain why they are collaborating in certain ways? Fairness is also a topic in the sense that, are we able to ensure that agents carry the same workload as they go about coordinating and cooperating towards higher level goals? And finally, what is the impact of heterogeneity when we're considering not only homogeneous systems, but agents that potentially are running different policies, or agents that have varying capabilities and skill sets? With this, I'd like to thank all of my team, and as well as my funders, supporters, and also the reviewers, all of whom are often on this. So thank you all, and thank you for your attention.
Thank you so much, Amanda. And I'm so sorry to interrupt you, but it was lovely we got to see the videos because they were beautiful. So it was very nice to see them in full resolution. I was just wondering, coming back to Kirstin's talk a little bit, have you explored at all the coupling between the environment or changing the structure in the environment and the emergent communication that comes out of that at all? Is that something you've touched on at all?
That's an amazing question. It's a very, very exciting question. So we don't actually have research or any published results on that, but I think that your intuition is spot on in the sense that the environment can provide incentives that can work towards achieving more or less collaborative systems. I mean, the simplest scenario is you can consider road networks. The more lanes you provide the cars, the more cooperative they will be because of the stakes at hand will push them towards less competitive behavior. If you only have 1 or 2 lanes, they will be competing much more towards, well, who actually gets to overtake or who gets to get home the quickest. And that will definitely have an impact on how the agents decide to cooperate. So that's maybe one simple example that hopefully illustrates a little bit how the environment does have an impact on whether or not agents coordinate or collaborate.
Brilliant, thank you very much. And yes, please do put your questions in the chat and we will come back to them when we have Amanda and the rest of the panel together later to discuss more. But thank you so much, Amanda, for your talk, and yeah, we'll come back to you briefly.